Hello and welcome to a simplification of the action potential. This short film video is presented by Dr. Lana Jones, which is me. So the action potential is the momentary reversal of electrical potential that is the basis for signaling in neurons. And don't let these words get too caught up in your head, right? The action potential is really just the electro part of electrochemical neurotransmission. So remember, the brain and neurons are signaling each other. That's neurotransmission in the brain signal. Electrochemical, the action potential represents the electro part, and the chemical part is represented by neurotransmitters, which are chemicals, neurotransmitter release. So some key terms that are involved in the action potential are the resting membrane potential, which we're going to talk about next. Remember, sodium and potassium ions are involved. There's words that we're going to discuss like stimulus and threshold and refractory period. Also, depolarization, repolarization, and hyperpolarization. So quickly, depolarization is just the membrane going negative to more positive. So think of dipole, more positive. Repol is going from positive back to negative. So repolarization is coming down in this side over here. So we have the dipole, the rise, to a positive millivolt level, and the repol, where you'll see this figure very commonly, where on the y-axis you have the voltage across the membrane, and on the x-axis you have time. So we have a rapid depolarization followed by a repolarization. When the line drops down below that -70, we call this the refractory period. This is also called hyperpolarization. Okay, so all of these terms are very important in understanding how the action potential works. And then finally, we have this thing called the sodium-potassium pump. But before we go on too far, let's first talk about the resting membrane potential. So when the neuron is at rest, it's sitting at -70 millivolts. That's a resting membrane potential. That means nothing has perturbed the cell whatsoever. There's some important things that are going on in the intracellular and extracellular space that cause this very specific membrane potential. So when we say membrane potential, it's the change in the electricity across the membrane. That's what we mean by a potential. So this has to do with the ion gradients. So extracellular means outside the cell, and intracellular means inside the cell. So it turns out we have more sodium on the outside of the cell compared to the inside. Okay, so this is a gradient. More sodium on the outside, and that's represented by this little Na+. There's also more chloride on the outside, Cl. So sodium chloride actually forms together to make salt. So imagine we want to have salt more on the outside, because if we had more salt on the inside, that would actually make the cell pull in water and swell up. So it's like if you were to eat something really salty, you kind of get bloated. So we don't want too much salt on the inside or it will bloat the cell. So we keep it resting with the salt, sodium chloride on the outside. We have potassium, which is represented by the K+, more on the inside. It's also a more negative charge on the inside, so that's represented by this little negative here. So positive on the outside, more negative on the inside. So the difference in these two is how we get our -70 millivolts. Again, that's the -70 millivolts across the membrane. So what causes the action potential? Well, the action potential is actually stimulated by the release of neurotransmitters. So neurotransmitters are released into this gap, right? These neurotransmitter molecules bind their receptors on the postsynaptic cell, and if enough receptors bind, this changes the polarization just ever so slightly. We just need a little bit to reach our threshold, and this will cause the action potential to fire. So again, neurotransmitters are released, they bind this postsynaptic receptor cell, and that causes an increase in the threshold of the membrane potential, which ultimately responds to a firing of an action potential. The action potential mechanism. So we're back to our little graph, right, where we've got voltage on the y and time on the x. So the first thing that happens is sodium channels open here. So you see, actually, you have a stimulus, and that's the stimulus we just talked about, right? Those neurotransmitters. So if there's not enough neurotransmitter, it just fails. Once you get enough neurotransmitter to bind to change the membrane potential by just 15 millivolts, you increase it by 15 millivolts, you hit threshold, and boom, this fires the action potential. This causes sodium channels to burst open, sodium rushes into the cell, and this causes the distinct rapid increase in the curve towards the positive voltage. This is our depolarization. Number 2, sodium channels close back up, and then our potassium channels begin to open. The third step is that potassium begins to leave the cell along its concentration gradient. So remember, there was more potassium inside. So now the positively charged potassium is leaving. So now the cell membrane is becoming more polar or more negative. We call this repolarizing. So it's returning to its negative voltage inside the cell. Number 4, we have our potassium channels closed, but they're kind of a lag. There's still a little bit of potassium that leaks out. So even after the potassium channel closed, the cell actually goes to negative inside, and we call this the refractory period. And that refractory period means that with stimulus, you're not going to fire another action potential, and it just actually allows the membrane to reset. Finally, getting back to its resting state, the sodium-potassium pump works to regulate the proper balance to recreate this resting membrane potential of negative 70 millivolts. And then that part of the axon is ready to do the whole thing again. So I hope this little video has been helpful in learning about the action potential and the mechanisms involved. Everybody can do neuroscience, and I'm here to help you all figure it out. Thank you.